So welcome everybody to this Sun Space Industry webinar. We have Paul Madle here today from KISS Space talking to us about space software engineering.
Okay, so welcome everyone. I'm Ian Rapus. I'm one of the co-chairs of the Space Universities Network. So I'm just going to take you through a brief introduction whilst a few more people join, and then we'll move straight on to Paul's talk. So if you want to move on the next slide. So just to explain a little bit about who is Sun and what these events are about. So the Space Universities Network is a group of higher education institutes across the UK that have come together because they are passionate about space and the education of our students in all kinds of aspects related to space. So we want to develop you as kind of skilled graduates through sharing best practice, relevant curricula, and generally promoting space science and engineering. The Space Universities Network is a network for tutors and academics within universities. So it's not open for students to join it, but you are benefiting from your tutors from being part of this network. And we have this set of resources that we have made available and share amongst the people in the network to help them develop their teaching around space-related subjects. You, of course, have, if you're interested in space, there is the UK SEDS network, which is specifically for students to join, and SEDS are on part of our Space Universities network, so we have the student link through having UK SEDS as one of our members. Okay, great.
So thanks everybody for joining and for putting what university you're from in the chat. We're lucky enough here today to have Paul Madle with us. He's a software engineer from KISS Space with over 20 years experience developing safety critical software and electronics on board both spacecraft and aircraft. He has worked on a wide range of projects from aircraft cockpit display systems, website development for business, and writing mission critical code. Together with a core team, Paul was awarded the Silver Team Award and the Jeffrey Pardreau Space Award for their exceptional contributions to the field of space. This webinar will be about a 30-minute presentation from Paul, and then we'll open the floor up to you guys for some questions. So do remember to put your questions in the chat as we go along, and we'll get to them at the end. Just so you know, this session is being recorded, and that also includes the chat as well. So I'll now hand over to Paul to start his presentation.
Thank you very much for the Space Universities Network for inviting me to speak on what I'm speaking about. And there's going to be two main parts to it. One where I'm going to be explain to you what the open source satellite program is, and see if you might be interested in engaging with what we're doing with that program. And then just a presentation about my area of specialism, which, as Charlie said, is embedded software, and how we can write software for spacecraft that works, which is quite important, as we'll find out. So, as Charlie said, my name is Paul Madle. I'm a senior software engineer, and I work for a company called KISS Space Systems. And we're a consultancy business. We provide consultancy in anything related to the space business, to small companies right the way through to big multinational companies. And we're heavily involved with a number of things. Most exciting right now is probably the work we're doing with Virgin Orbit. And you might have seen we're trying to launch space rockets. We've been doing some 3D printing today, so I thought I'd show you some 3D printed models of Launcher 1, which is the rocket on board the hanging off the bottom of a Boeing 747. And we're also involved with the development of a satellite called KernoSat-1, and we've been doing again more 3D printing. I got very excited with the 3D printer earlier on today, and here's a mock-up of our of KernoSat-1, which is going to be flying on the Launcher 1 rocket next year, hopefully. for the second launch out of the UK from the Cornwall spaceport. And hopefully this time it works. I can assure you the first failure was nothing to do with me, before we get too much further. But yeah, so if I can explain to everybody here about what we're trying to do, first of all, with the open source satellite. So by way of introducing it, there's a quick history lesson. So when we started putting things into space, things were very expensive. Launches were very expensive, and because launches were very expensive, there was a real sort of drive to make the technology put on spacecraft to be as reliable as possible. We didn't want to launch something that wasn't going to work. So in order to make it reliable, it had to cope with the space environment. So we started launching things that were inherently designed to be good for the space environment, good radiation properties, because space is a high radiation environment. And because we were using those kind of technologies, the spacecraft tended to consume a lot of power and electrical power. And so it needed a lot of, solar cells, and it needed to be rather big. So the bigger the spacecraft, the bigger you make your spacecraft, the more expensive it is to launch. And so if you wanted something with a fair degree of performance, you needed to pay a lot of money. Now, in the 1980s and going into the 1990s, there were a group from the University of Surrey in the UK that were formative in bringing about a bit of a revelation in the space industry, a disruptive technology. And what they were doing is basically taking technologies that you find in your car or your mobile phone or your laptop computer and launching them into space, which at the time was quite novel and quite sort of, people thought they were a little bit crazy because these technologies aren't going to survive the space environment. But it turned out that they did, particularly in low Earth orbit. So not as high as geostationary perhaps, but certainly within low Earth orbit, these things can be quite reliable. And what's happened over the years is that there's been a revolution, another revelation to the CubeSats. So CubeSats are a standardized form factor for a very small satellite that uses commercial off-the-shelf technologies extensively. And so this has been great. It's been great at bringing down the price of entry into space. But there are problems with it. One problem is reliability, and I'll discuss that a little bit more later on. Another problem is the fact that you can't break the laws of physics. There is a limit to what you can get a CubeSat to do because of the nature of it being very small, being a 10-centimeter cube. And so there's a push within the industry to do something to kind of go somewhere in the middle. So take the capability of a small satellite that would be then developed by the likes of companies like Surrey Satellite Technologies, and make those things cheaper to manufacture, to produce, and basically create a new market. There's this market need in this kind of area of the space market, the satellite market. So we thought, right, let's design the next generation of microsatellite. With the aim of trying to make a small satellite cheaper to produce. So we looked around and we thought, right, how can we do that? How can we make a design, cheaper? How can we make it easier to enter the space industry with a more capable satellite? And so we looked at the world of open source. Because with open source, as you no doubt know, you don't need to pay a license fee for the development tools, for the software, for the hardware, etc. And there's plenty of, particularly in the software industry, there's a lot of open source technologies that have got a lot of credibility and have shown to actually be competitive to their sort of commercial counterparts, the likes of GNU that create compilers for your programming languages. That are now kind of like the de facto standard for compilers across the world. And then there's real-time operating systems like FreeRTOS, which are now prevalent across lots of embedded applications worldwide. And then there's Linux, latterly, we've started to open source the design of hardware as well. So the likes of Arduino, SparkFun, Adafruit, all of these kind of organizations are open sourcing not only software, but also electronics hardware as well. So what we want to do is open source the design of a satellite. So we're developing a satellite, and in fact, this KernoSat-1 that I was talking to you about earlier on, with its deployable solar panels, etc. This will have on board the first part of the open source satellite intellectual property, which we're releasing open source. And the main brain inside this satellite will be the computer, which is the computer that we're developing for the open source satellite. So if you want to get involved with that, there'll be some slides towards the end of this presentation where you can register your interest in getting involved with the development of the open source satellite. And we have people who have no software experience. We have people who are graduates. We've got people like yourselves, or students. We've got people at the end of their career, having 40 years experience in the space industry, and everything in between. So and right the way across the world as well. So it's an exciting thing to be involved with. I'm enjoying it a lot. My particular specialty is software, and so I'll move on to talk about software in space. As I said, I've got about 20 years experience developing software for embedded platforms, mostly sort of critical platforms that are used on aircraft and spacecraft and medical devices and things like that. But the way I started my career was actually working for a new space company. So before I talk about the new space and traditional space industry, let me give you a little bit more of a history lesson when it comes to software in space. And actually, it was the space industry that innovated software in the first place. When we were doing the Apollo missions, we had women. They were heavily involved with the development of the sort of first programs that were used by the Apollo programs. And Bell Labs were a critical company that were, inputting into those missions. So, from those early stages, it was quite sort of female dominated, and actually became a very male dominated industry, the software industry, for quite a while. And I'm glad to say that now we're redressing the balance, and certainly where I sit today, working for KISP, the technical staff of 50-50 male female. So we're redressing the balance. But anyway, Bell Labs went on from those Apollo missions to develop programming languages, and probably the most significant one that they developed was the C programming language, which is kind of considered to be the kind of godparent of, or the grandfather of most modern programming languages. But that's where the exciting bit in terms of how space influenced software really stops, because there's a limit to what the software that you can run on a spacecraft, and the limit for many, many years has been the computing power. So the computers that you tend to put into spacecraft tend to be behind technologically from the kind of computer that you're listening, that you're on right now, whether it be a mobile phone or a laptop or a desktop or whatever. The commercial off-the-shelf processors like your Intel i7 type processors are way ahead in terms of processor power and processor grunt from the kind of technologies that we tend to fly in space. And that's been because of the radiation environment in space. So one of the problems with space is that you have this heavy, well, relatively heavy radiation environment that degrades the silicon inside a processor over time. And there's effects like what are called single event upset. And that's basically where you have high energy particles hitting the silicon inside your processor and causing bits within your silicon to flip from 1 to 0 or from 0 to 1. And software doesn't like that very much. It doesn't really work very well if the memory inside the processor changes its state randomly. And so what the tendency's been to make use of radiation tolerant and radiation hardened technologies. Now, up until recently, those technologies have been really behind the curve in terms of processor power, processor grunt. But recently, within the last sort of 3 years, companies like Microchip have started producing radiation tolerant and radiation hardened components that are relatively powerful, still not, as powerful as your Core i7 type thing. But these are based on ARM microprocessors and that kind of thing. But also what's happened is that, as time's gone on, we've been developing processors, microprocessors that have transistors in them that have got smaller and smaller and smaller. And the reason they're getting smaller is because we want to make them quicker and quicker. Now, one of the downsides of making the transistors smaller and smaller is that eventually they become very, very, very small, and the amount of energy required to cause a bit flip from a 1 to a 0 or a 0 to a 1 is far, far less. And actually what that's meant is that the kind of effects we see in space of bit flips in the silicon are now occurring on the ground. And there's examples of this, so you can Google it, but I think there was an election in, I think it was Norway or Sweden or Scandinavia somewhere, and they held this election and they did the voting. They did the voting with computers, and during the election there was a bit of an anomaly, and they didn't expect the winner to win the election, and so they reanalyzed the votes, and they found that there was a discrepancy between what the counting computer had said and the actual votes placed. And they poured through the software. They thought there must be some bug in here that is causing this to happen, and they couldn't find any problems with the software. And they looked at the discrepancy, and the discrepancy was 1,024 votes. And when they looked into it a little bit more, they thought, well, that's a power of 2. So maybe there's been, a bit flip in the silicon of the processor which was counting the votes. And that was the eventual sort of, the conclusion that basically the sun's radiation was causing bit flips in the silicon of the computer that was counting the votes. So this has caused, this kind of effect, has been the blame for power outages in power networks across Canada, and all kinds of things on the ground. So the semiconductor industries had to cope with it, not just on radiation tolerant components, but also on commercial off-the-shelf components as well. And so many processors are now being produced that have inherent properties or sort of hardware features that allow them to be tolerant to this radiation effect. And this means that we now have the possibility of flying more and more faster, more clever, lower power processors in space. And that means that we can write exciting software for spacecraft to do more things. So the other thing that is kind of topical software-wise in space is the idea of a software-defined satellite, or basically a lump of hardware that is a satellite. You put it into space, and then you get it to do different things based purely on the software that's running on it. So it's kind of inspired through, in the business world, what we call software as a service. And there's also other innovations. There's new programming languages that are becoming trendy. One is called Rust, which you may have heard of if you're into, coding type stuff, which is kind of taking the foibles of some of the more traditional languages like C and C++ and creating an embedded kind of language that that is a bit more, has safety in mind from the ground up. Python's also being used in space, not very typically, but there's certainly instances of that now that the processors are becoming more powerful. And there are new tools as well. So tools like SysML, UML, autocode generators using Simulink, Stateflow, and that kind of thing. These kind of tools are being used, particularly for the attitude control algorithms and things on spacecraft. These tools are being used, and new processes. So one of the trendy words in the, you know, or a couple of trendy words or keywords in the software industry is agile and DevOps and that sort of thing. And those kind of approaches are coming into the space industry as well. And I'll describe that a little bit as I go along as well. But largely the space industry is split in two, really. You've got your traditional space industry. That's the likes of the European Space Agency, NASA, JAXA, all of these kind of agency type organizations. And you have the new space industry. And some people would say, well, this is the old way and this is the new way. And with the traditional space industry, you tend to have quite heavy processes because they want high reliability. They're using public money. They want to make sure that whatever they fly will work, which is fair enough. But the downside of that is that the development times of the software are very slow. Well, not just the software, but just the whole thing is quite slow to develop. The new space industry, the likes of CubeSats and that kind of thing, have low or even no process behind how the spacecraft is developed. It tends to have a low reliability as a result, but the benefit, obviously, that it has a fast development time. So what is optimal? Because in my experience of developing, you know, to stringent standards and stringent processes, is that actually, you know, the upside is you end up with something reliable, but the downside is that sometimes you end up following a process because, you know, you are told you will follow this process. Don't think about why, just follow it because the process is always right. And that in some senses can be a little bit dangerous because, you know, you always really need to ask yourself, well, why does the process exist? And, you know, is what I'm doing sensible? If you look at the new space industry, anecdotally, I was talking to someone the other day about CubeSats, and they said, well, you know, the problem with CubeSats is that 1/3 of them, they get launched into space and they don't work at all. They don't do anything. They are just lumps of stuff up in space and they just float about. Another third work for, you know, a week, a month, maybe even a year, and then die. Or, you know, there's software bugs, there are problems with the hardware, there's just reliability issues. And then another third, the final third, actually go on to do something and do what is intended by the mission. So, you know, there's a problem here because really what we're doing is increasing the amount of space junk. And, you know, if you know much about the space industry, you'll know that there's a lot of space junk up there. So what can we do to be optimal somewhere between these two? So when I came back into the space industry, having been out for a little while, doing lots of safety critical systems for aircraft and all sorts of other things, I thought, right, we need a new process. You know, we need to define a process which will work, not cost too much money, but will ensure that we get software that works. Because when things go wrong, they can be disastrous. In 1996, the first Ariane 5 rocket exploded due to a software bug costing $370 million. So this was actually, the bug was traced down to a 32-bit number. It was just counting up, you know, 1, 2, 3, 4. And in the code, it was being put into a 16-bit number. So it's something that happens quite commonly. You know, someone who's not got a lot of experience of writing software, that's a common bug, you know, using the wrong type. And that was the result. It exploded. And then in 2021, July 2021, is just two examples. The ISS, the International Space Station, lost attitude control, and Russia blamed a software glitch. Russia had one of the subsystems on board, and that was the blame. So, you know, it's going to have catastrophic, you know, effects. And the other problem is that, you know, I mentioned earlier on this idea of a single event upset. That's where high energy radiation causes bit flips in the silicon. And the problem is that these bit flips can be, you know, if your software goes wrong, if you ask a company, what went wrong with your satellite? Instead of saying, oh, our software was wrong, or there was a problem with our electronics or something like that, they can easily say, there was a single event upset. And that's what caused the problem on our satellite, which sounds like a random event. They had no control over it, and it's an easy thing to pin the blame on. And just for interest, if you're interested, you can see a map of the Earth and where single event upsets are seen in low Earth orbit. And there is actually an area around the South Atlantic called the South Atlantic anomaly, where you see a lot of these bit flips in silicon. So these are some measurements that have been made over time. So it's a real phenomenon. It really happens, and it's easy to blame things on single event upsets, which are actually sort of poor engineering practice and that kind of thing. So how do we write code that works? How do we do that? Well, there are different standards that exist. The European Space Agency has the ECSS processes for software development. They've got ECSS processes for all kinds of things, systems engineering, the way that you hook your wires together, the connectors you use, all of these kind of things. But they also cover software. And there are two standards, ECSS STQ80 and E40. And they've been they've borrowed processes that were created by the aerospace industry. The Federal Aviation Authority, quite a long time ago now, created a standard called DO178, or guidelines, or a sort of something that needs to be certified against, and that's a standard which is used on aircraft. And then in medical devices, there's EN 62304. Now, all of these sort of standards or regulations really point at similar sort of things. And so when it came to the open source satellite, I thought, right, okay, let's adopt some things which add value without creating too much process and costing too much money. So all of these processes, they talk about the need for a life cycle, a software life cycle, nothing particularly earth-shattering there. But this is the one that we have for the open source satellite. But essentially, there are phases of writing the software. So in the software domain, you'd create requirements, and then you'd create a design to against those requirements, and then you write code. So you don't just go in and hack code. You're a little bit more purposeful about it. You have requirements, design, and then code. And then on the other side of what we call the V model here, you have unit tests. And unit tests follow the design. They are ensuring that the code does what the design says it should do. And then you have integration tests, which are following the requirements. They are ensuring that the software does what the requirements say it should do. And in our sort of software development approach, what we do is kind of this iterative life cycle. So we don't know right at the beginning what all the requirements need to be. To do that, to say that you do know, is a little bit naive in my experience. And so what you do is you take off a lump of functionality and you say, I'll define the requirements for a lump of functionality, and I'll refine my design on that basis, write some code, write some unit tests, and then I will demonstrate something. And then I'll come back up to the beginning again and refine my requirements again, and do some more design and do some more code, and then go around in this kind of loop. Loosely in this software industry, this is kind of referred to as kind of agile methodologies, or basically iterative. So you don't know everything before you start. You just kind of do a little bit and then do a little bit again. And this has been widely adopted in the software industry over the last number of years, and it's creeping into the space industry as well. So taking each part of this life cycle in one by one, if I start off in requirements refinement, it's important to write good requirements. And I've just given you a quick example of what I consider to be something that's good. So you can write your requirements in structured written language, and one of the important things about doing this is to ensure that your requirements are what are called atomic. They describe one thing. So in this example, the spacecraft software shall accept a telecommand to add a file to a downlink queue, blah, 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 right? So the important thing about this is that it's saying one thing. It's not saying the spacecraft software shall do this on Tuesday and that on Wednesday and that on Thursday, if this, but that, and, in this huge, long sort of spiel. And the reason that we do this, the reason we want to break them down into atomic statements that are structured, is because when it comes to the test, when you want to test the software, you know, reading this, it is very clear what a test needs to be against this requirement. The sunny day scenario and the rainy day scenario. So, you know, if as I've sent this telecommand, I want this downlink queue to be modified. If I don't send the telecommand, I don't want it to be not modified. It's clear. It's clear what the test would be. There's metadata that you might want to attach to a requirement as well, like its rationale. Why does it exist? And that can help people to understand when they want to question a requirement. Then there's you know, various bits of other metadata, but critically, one of the things that you need to define is the test methodology. Think about the way you want to test the software at the point you write the requirements. That will lead to better tests and better software. So the next stage on, you know, in writing code that works is the design. So use diagrammatic tooling to model your code. You can use the unified modeling language or MATLAB Simulink for algorithmic type software, and you know, create diagrams, create design artifacts that help you to understand what it is you need to do. Then on the coding side, when you get down to the code, use languages which are simple. C, Rust, Ada, these languages are very close to the ones and zeros of the computer. Avoid complex programming languages like C++, C#, and Python, because these languages, you know, as you write your code, it's harder to translate from your code to the underlying ones and zeros that get executed on your silicon. So it's difficult to prove that this code works, easier to prove that this code works. Then use coding standards, for example, MISRA or Spark Ada. Personally, I find that horrible, but you know, MISRA is a good example. Basically, it's a way of restricting your language down to a safe subset of the language. And most coding standards restrict the use of some of the more dynamic behaviors of runtime you know, that make your code more deterministic. Another thing to consider is to make your code units, whether it's functions, methods, whatever it is, simple and straightforward, and that will make it easier to test and to understand and maintain. Going on to the test side of things. So you can perform unit testing, which is basically white box testing. That's basically taking, you know, let's say you write your code in C. So you've got a C function and you take that C function, you take it out of your executable, and you fire inputs at it and you observe the outputs from it to check that it works as expected, as per your software design. And when you do that, there are tools that you can use. GNU compilers have something called gcov that allows you to monitor the code that is being executed as you run your tests. So, you know, how many times have I hit this line of code? You know, this is output from gcov. So you can see what code has been executed. And the idea here is to cover all the bits of code that you haven't tested, because there are lots of bits of code. If you run a test, the chances are you're not going to execute every line of code. And it's not till you look at the code coverage that you discover the bits that you haven't executed. And those are the bits that are going to go wrong once in a blue moon in orbit. And then finally, the final part of your testing is integration testing. So treating your software like a black box, like a lump of code that's running on some piece of hardware, and you fire inputs at it and you observe the outputs. And you look at your requirements, the requirements that define what the software needs to do, and you set your inputs in range and out of range to check that the software doesn't crash, and observe the output with those inputs. So kind of two forms of testing, really: unit testing and integrated testing, white box and black box. And then another trend, which you know, is typical within the space within the software industry at the moment, and is being adopted by the space industry, is continuous integration. And this is actually our continuous integration workflow on the open source satellite. So if you work on the open source satellite and you develop code, critical code, You'll develop it in an integrated design environment. You'll write your code in this environment. Then you might, upload that to GitHub, which is a sort of open source repository for loads of open source code. And then what we have is a sort of agent, a software agent running in the cloud. It picks your code out of GitHub, compiles it using the GNU compiler, and then actually executes it on a real physical piece of hardware, which is actually located in the room 2 doors away from me in our lab in Farnborough in the UK. And when it executes the code, it will produce results. The idea here is that you'll see the results of all the tests of the code as you go along. So if you've ever written code, what this is designed to do is to stop the whack-a-mole effect. So the whack-a-mole effect is basically where, you write your software, you find a problem, and the problem's here. So you whack it down, you debug it and you fix it. So you whack it down there. What you're unaware of is that by doing that and fixing it that way, there's another problem sprung up over here. And unless you know about it, you don't know to whack that one down and find the next one. This approach allows you to see the problems that you've introduced as you write your code, and reduces the amount of bugs that get through and into orbit. So that's really kind of my breakdown of what makes good software engineering practice for spacecraft. My take on the new space industry and the traditional space industry, and where we sit in the middle with the open source satellite. So yeah, thank you very much for listening. If you are interested in getting involved with the open source satellite, then please, register interest on our website. You can get hold of us through our website, through LinkedIn, Twitter, email. You can even phone us, or you can send us a letter. I'm not sure that really happens anymore, but you're welcome to. So thank you very much for listening. I think there's now a little bit of time for questions and that kind of thing. So I guess I'll hand back now to Charlie. Shall I stop sharing at this point, Charlie?
Maybe you could just leave the last slide up that sort of
Okay.
shows all the ways to contact
Yeah, sure.
That was really great. Thank you very much for that. It was a really great presentation. So if anyone's got any questions, please do post them in the chat. We have a couple, and yeah, we'll just go through asking them now. So you've talked a little bit about how the industry has changed with the history section. Could you express a little bit more about where you see it going in maybe the next 15 to 20 years? Yeah,
I mean, in terms of the capability of spacecraft and the way that we're able now to put more high-end microprocessors into spacecraft because of the changes I described, and the way that's affecting what we can do. Right now, there's a big push to do a lot of processing on the spacecraft. So let's give an example of an Earth observation mission. So this is a satellite that takes pictures of the ground from space, a very typical use case. Typically what we would tend to do is take this massive image, gigabytes of data, and download that over a radio link. And that radio link has a limited bandwidth, so it takes a very long time to get all that data down. So the limiting factor there becomes the bandwidth of the radio. And one way about getting around that is, instead of downloading the entire image, you might want to do some processing on board. So, for example, if you were interested actually in the location of a bus, or where the buses are in the image, or the location of a hurricane, or some feature on the ground. Most of the time up till now, we've been downloading images and then taking that data and then doing some post-processing on the ground. Nowadays, we're increasingly getting the capability to do that kind of processing actually on the spacecraft. So if you wanted to find out where the buses are, we could take that image, do some direct processing using high-end GPUs, high-end embedded GPUs on the spacecraft, find the locations of those buses, and instead of downloading the entire image, now all we have to do is download the location, the coordinates of those points of interest instead. So, we can then do things in a lot more efficient a way and get more of the interesting data down from the spacecraft. So that's one example of where, the industry is changing. Is that a good answer?
Yeah, that's great. That's really helpful. So we've got another question from Jason from the University of Nottingham. They said, interesting talk, thank you. No formal verification used though, still using manual testing.
Yeah, we are for the open. Yeah, well, what we're doing is creating tests using on the open source satellite. We're using a technology called CMOCA, which is an open source test framework. You have to manually create the tests in C code, but then rerunning them is automatic. So you make a saving. You have to sort of invest in the first mission. To get all of this going is an expensive thing to do. But once you have it going, and your second mission and your third mission and your fourth mission, you're just rerunning this stuff all the time. So it becomes a lot more efficient. And SpaceX actually, one of the things that they're obviously very good at rapidly changing, rapidly turning around changes in their code and that sort of thing. And the way they do that is with continuous integration. So yes, it's not, I think, as you say, formal methods. It's a more sort of, it is this way of doing it. There is automation in the fact that we're using unit testing tools and software that makes writing the tests easier, but it's not fully automatic. I'm yet to find a tool that, certainly not an open source tool, that you could sort of throw code at and it produce decent quality tests. That would be great, but I'm yet to see it.
Cool. Now we have another question from a different Jason, and they've said, what are good coding practices that should be applied to software, and what are some that may differ from other software industries? And great talk, by the way.
Oh, thank you. Yeah, I mean, I think largely the standards which you should apply to your code. Let's say it's C code. So coming back up to this slide, we were talking about where is it? Here. Yeah. So MISRA is basically a definition of a subset of the C language. So it says, do this, don't do this, do this, don't do this, that kind of thing. And it's actually coming out of the automotive industry, and it's directly portable to any C code if you want to make it reliable. So there's a lot of crossover between different industries. The only real thing that is different between other industries and the space industry is the raw power of the silicon. You're limited by the power of the processor. And the other issue, which is kind of unique, is the radiation environment. So there are things that you might want to implement in your software to mitigate the effects of radiation, the single event upset that I described, and that kind of thing. But those are really the only things that are specific to the space industry, I would say.
Are general purpose programming languages used in space systems in orbit, or is it all proprietary languages even now? No,
there are lots of, I would say probably C is probably the highest, that language is probably the most common. But there are, lots of different languages, less so the proprietary ones. Most people use C or C++. There's some Python. I think there's even JavaScript running on, I think some of the SpaceX manned missions and things like that. So there are different languages being used, but they're all pretty sort of common, really.
Do you have any recommendations for students who maybe didn't study computer science at school or are new to coding, and what languages and tools do you recommend?
Well, I guess, yeah, I mean, if you wanted to learn C code, I would recommend, for embed. Let's say you wanted to just get into, in writing code that looks a bit like code that would run on spacecraft. Arduino is probably the best point to start. So, these kind of Arduino kits that you can buy, and they're quite cheap. You can buy a kind of I wish I had one. I have one at home, but they're kind of like, little computer boards that you can write C code on them and quickly get that C code doing things to control robots, to control all sorts of different things. And the technology you'd be learning there would be the same kind of technology that is transferable into embedded software for loads of industries, and space being one of them.
Cool. So I have a question from Lisa. She says, thank you so much. This was a really interesting talk. I was wondering if the open source code of the satellite makes it more likely to be hacked, and if so, what measures are taken to prevent it?
Yeah, so in the communications between the ground and the spacecraft, really truly and honestly, the space industry is in its infancy when it comes to cybersecurity. There is, in the communication standard between, the ground and the spacecraft. So there is some encryption and authentication which goes into that sort of software, where you need a key in order to access the spacecraft and stuff. It doesn't prevent denial of service attacks and that sort of thing. But well and truly, the space industry is very much in its infancy. In fact, I think there was a YouTube video I was watching the other day of I think it was one of the Falcon rockets, and someone had actually just built a fairly rudimentary software-defined radio for the ground, and a hobbyist had created this, and they were receiving the telemetry data on the radio off the rocket, and they were able to decode that and get the video feeds for themselves of the fuel tanks and all kinds of stuff like that. All of it was completely unencrypted, so it's completely plain text. You could just read it, and some of it was actually in ASCII as well, so you could even sort of read the text, like I don't know, onboard computer temperature 20 degrees. You could read it like that. So so yes, we're very much behind when it comes to cybersecurity. There is some efforts to secure the information going up and down onto the spacecraft, and on the main way we're going to do that is with encrypting the downloaded data using AES 256. But as I say, we're not big on this in the space industry, in all honesty.
Cool. So yeah, we've got a few more questions in the chat. And we're starting to run short on time a little bit, so we might need to shorten the answers slightly.
Sorry.
So we've got a question from Vilius. Would more advanced high-end processors create any additional thermal issues?
Yeah, they can do. I mean, basically, as time's going on, not only are the processors becoming faster, they're also got better thermal properties as well. But yeah, thermal is an issue. So what we're putting on the open source satellite as a main onboard computer is an ARM M7, which is a kind of mid-range ARM processor. It doesn't get too hot.
Cool. So we've got a question from Arion from the University of Manchester. She says, very interesting and informative talk. Does the industry currently use or will be using AI in solving code bugs to produce efficient code, which will pull down chances of errors close to zero? Just giving an everyday example like ChatGPT.
Yeah, quite possibly. I'd love to see that. I'd love for ChatGPT to be able to debug my code for me. Actually, I tried it the other day. I actually tried to get ChatGPT to write some drivers for the processor that we're using, and I wouldn't want to use the code it created, but but it certainly is an amazing tool, and the technology is getting there, isn't it? Where we could do that kind of thing. So that would be really cool.
Nice. So we've got a question from Jamie saying, very interesting talk. What are you looking for from current undergrads to contribute to the open source satellite program?
Just, time. We need people with a bit of time. We need people who are interested in space, interested in embedded systems, and interested in learning about software and learning about spacecraft and the onboard software within it. So probably in terms of skills, C code.
So Daniel said, enjoyed the presentation. Great to see C language being used. I had been considering this idea in reintroducing it to our students. I'm now definitely going to do it.
Oh, excellent.
Daniel. And one from Ashok saying, great talk, Paul. Thank you. You mentioned mitigating single event upset via software guide rails. Can you give an example of how to check for bit flips?
Yeah, I mean, it's not very nice to do it in software, in truth. The way we've done it is much better to do it in hardware. That's for sure. So typically in hardware, you do it via either basically having two bits of memory and or 3 bits of memory, triple memory redundancy, and some kind of voting logic implemented in hardware that kind of does voting on the data coming through to the processor. So the software has got no idea that there are 3 memories. It sees 1, but actually there are 3, and there's some voting going on in hardware. If you had to do it in software, and I have done it in software, but it's not nice, is to basically triplicate your variables and then do voting in software. That's not very practical in truth, but it can be sort of semi-done, but it's not very good.
Cool, thank you very much. So I think that's the end of all of the questions, unless anyone's quickly typing one down now. Yeah, I think we're towards the end of all the questions. So thank you very much, Paul, for joining us today, and thank you for a great presentation and going through all those questions.
Yeah, thanks very much, guys. I'm glad there were lots of questions, and yeah, good luck, everybody.
Great. Thanks very much, Paul, and thank you to everyone for joining our webinar today. And we hope we'll see you at future ones.